Hi everyone. Today we are going to talk about reduction. We will use reductions a lot in CSE 331, but many people may not have seen it formally in other classes before. In this video, we will go through an example of reduction to explain what is a reduction and how to use reductions in CSE 331. What is reduction? It's basically modifying the question we want to solve so that we can use solutions, algorithm, code library we already know to solve the modified problem. We have done something similar to this before. In this video, I'll be using Python format for pseudocode. Back to the first day, where implement your first sort function, which sorts numbers in ascending order. We'll write another function from 0 again if someone asks you to sort things in descending order. Some people simply negate all the entries in array A and negate them back after calling the exitSort function to sort the array. This is correct because sorting negation of numbers in ascending order is the same as sorting the original numbers in descending order. And sometimes we need to preprocess our input data before calling the library function. The best thing about library function is that we don't even have to write our own sort function like mySort, because we all know that these library functions are correct and efficient. Another simple example is suppose we only know the formula for the area of a rectangle, which is base times height. And now we are trying to find the area of a parallelogram. What can we do? We cut and slide part of the parallelogram to convert it to a rectangle, and then apply the formula for the area of a rectangle. From this picture, we know that the base remains the same after we change the shape, and the height is just what it is. So the formula for the area of a parallelogram is still base times height. We use reduction not only to stop building new wheels, but most importantly, we use the correct algorithm we already have to make sure that our algorithm also returns the correct result. In this example, the algorithm is just a formula. In this course, we not only need to find the formula or algorithm for calculating the area of a parallelogram, we also need to prove that this formula works. More specifically, why cutting a parallelogram and constructing a rectangle is correct. But we won't demonstrate how to do it in this video. In this video, we will first discuss representing graphs in different data structures and give a brief overview of the BFS algorithm. Then explain the new concept, diameter, and define our question. We will also talk about how to use BFS to find the shortest path and how to perform the reduction here. Finally, we will present the overall algorithm and show how to prove its correctness in both incorrect and correct ways. Before everything starts, let's talk about how to represent the graph in different data structures to give a smoother transition from data structure course to algorithm course. Now we have an undirected graph, and the notation of graph is G equal VE. Obviously, V is a set containing all the vertices. But what about E? E means the set of edges, and usually we can represent this set in either adjacency list or adjacency matrix. Adjacency list means we store all the vertices adjacent to U in a linked list ADJ list U. In this example, blue vertex connects to green and red, so we can see both of them are in the adjacency list of blue vertex. Adjacency matrix means we store them in an n times n Boolean matrix or 2D array. We mark it as 1 if there's an edges from U to V, otherwise we mark it as 0. Here, green connect to blue, so in the adjacency matrix, both green-blue and blue-green are 1. However, because green and red are disconnected, in the matrix, green, red, and red-green are 0. There is some difference between these two graph representations. In the adjacency matrix, we can make sure whether an edge exists in the graph by simply checking if matrix UV equal 1, since matrix is just a 2D array. So the time complexity is big O of 1. But in adjacency list, we have to traverse the whole neighbor list of U to make the decision. So it takes big O of n. Here, n means the cardinality of the set V. The advantage of adjacency list is that usually it is faster if we want to traverse all the edges. You can see that the number of elements in the list can be less than 3, which is the number of vertices. So the time complexity here is big O of n sub u. N sub u means the number of vertices connected to u. However, we have to traverse all the index in the adjacency matrix, so it will always take big O of n. For the same reason, adjacency list representation usually use less space to store the data. It takes big O of m plus m space. M means the cardinality of the set E. The reason of m plus n is we need n amount of lists to represent the neighbor of all the vertices, blue, green, red. And we can see that in adjacency lists, each edge appears in exactly 2 of the lists. Blue-red, blue-red-blue, blue-green, green-blue. And 2m is equal to big O of m. In adjacency matrix, we always use a n times n size of matrix to store the data, so it's big O of n squared. In this example, we have 4 vertices A, B, C, and D. A connects to B, C, D. B connects to A, D. C connects to A, D. D connects to A, B, and C. We can see there's an edge from A to B, which means if we store the edge in the adjacency list, then B is one of the neighbors of A. Also, A will be in the edge list of B. If we store the edge in the adjacency matrix, then ADJ matrix AB equal 1 and ADJ matrix BA equal 1. Now we are going to do a refresher on BFS algorithm because we are going to use BFS in our reduction. Given a graph and a star vertex, first, we initialize an empty queue and an empty set. The BFS first visited the star vertex. Then we'll keep taking the first element out of the queue and mark all unvisited neighbors of this element as visited and add them to the end of queue until the queue is empty. Overall, the order in which BFS visited vertices is first the star vertex, then the vertices adjacent to the star vertex, then the vertices adjacent to those vertices but not yet visited, and so on, until all visitors have been visited. BFS uses a queue to ensure that the vertices in the graph are processed in hierarchical order. This is also covered in the textbook in section 3.3. Check it out for details. Suppose we have an example graph with 6 vertices with number from 1 to 6, and we have edges 1, 2, 1, 3, 2, 3, 2, 4, 3, 4, 3, 5, 4, 5, 5, 6. Now let's try to run BFS on this example graph. We start at vertex 1 first. Based on the code the arrow points to, we push 1 into the queue and add it to visited. Now the arrow moves down inside the loop. While the queue is not empty, current vertex equal queue dot pop. The queue is not empty, so we pop the top of the queue, which is 1. As the arrow now points out, for all neighbors of the current vertex, if the neighbor is not being visited, we push the neighbor to the end of the queue and add it to visited. 1 has 2 neighbors, 2 and 3. Since we haven't visited 2 and 3 yet, we push them to the end of queue and add them to the visited. Now we need to go back and check if the queue is empty or not. Queue is not empty, so we pop the top of the queue, which is 2. 2 has 3 neighbors, 1, 3, and 4. Is 1 invested? Yes, we just continue. Is 3 invested? Yes, we continue. Is 4 invested? No. So we push 4 to the end of queue and add 4 to visit it. Queue is not empty, so we pop 3 from the queue. 3 has 4 neighbors, 1, 2, 4, and 5. We already visited 1, 2, and 4, so we'll skip them in our for loop. Is 5 invested? No. We push 5 to the end of queue and add 5 to visit. Queue is not empty, so we pop 4 out. 4 has 3 neighbors, 2, 3, and 5. Since all of them invested, nothing happened in 4's iteration. Queue is not empty, so we pop 5 out. 5 has 3 neighbors, 3, 4, and 6. We haven't visited 6 yet, so in the for loop, we add 6 into these two containers. Queue is not empty, so we pop 6 out. 6 only have one neighbor, 5, and it's visited. Nothing happened in 6 iteration. Now the queue is empty. We visited all the vertices on different layer using BFS. Now let's look at an interesting new concept in graphs, diameter. This is a screenshot of a new power supply I brought on Newegg. 850 watt, a solid power unit enough for an NVIDIA 4080 video card and a 32-thread AMD CPU. Everything's great, but the seller is located in Ontario, California, not Ontario in Canada. And it takes over a week from California to Buffalo, New York if I choose free shipping. It only takes 2 days if I buy it on Amazon because they have warehouse all over the place. To get people to choose Newegg over Amazon, they have to lower the price and earn less. And that's why I choose Newegg. Fast is good, but I prefer the cheaper one. Suppose you are the manager of Newegg. You want to build some new warehouses in the state so that all of your customers don't have to wait so long and you don't have to lower your price and make less money. 2 of your colleagues have given you different plans for distributing the warehouses and have come to you for advice because you are the only person in the group who has taken CSE 331. You need to make the decision based on some objective. Remember, our goal is to reduce the wait time for customers who live far from our headquarters. So, suppose the way we determine which plans to choose is the one that minimizes the wait time for the farthest customer, like from California to Florida or Maine in this picture. Do you have a term for this property? And here comes the definition of diameter. Given a graph G equal VE, diameter is the maximum of distance between all pairs of vertices. Here, U and V are arbitrary vertices in the list of vertices V that are different from each other. Distance DUV means the smallest number of edges that we need to go through between these two vertices. After the explanation of diameter, now I'll define our new problem. In our question, each state is a vertex, and we add an edge with cost between 2 states if they are adjacent. To simplify the question, all edge costs are equal to 1. Here's the graph with the states around New York. I didn't make a graph of all 50 states because it will become too complicated. In this graph, New York connects to Connecticut, Delaware, Massachusetts, New Jersey, and Vermont. Connecticut connects to Massachusetts, New York, and Rhode Island. New Jersey connects to Delaware, New York, and Pennsylvania. Pennsylvania connects to Delaware, New Jersey, and Maryland. Vermont connects to New Hampshire, New York, and Massachusetts. New Hampshire connects to Maine, Vermont, and Massachusetts. And here's our question. Present an algorithm that take as input of graph G in adjacency list format where all edge costs are equal to 1 and outputs the diameter of the graph G. The algorithm should run in big O of V squared plus V times E. Argue the correctness of your algorithm and do a runtime analysis. Just in case, the vertical bar means the cardinality of a set. I will stop the first part of the works radio here while you think of a solution. Once you have thought about it, please continue with the second part of the works radio.